about kind of what we've talked about so far. We said that stars live their lives. A lot of times stars can be born in the same stellar nursery, basically what we call a molecular cloud, big old nebula, and how they live their lives depends upon mass. And so actually in chapter 13 we talked about a important mass of 8 times the mass of our sun. Okay, so anything that's less than 8 times the mass of our sun is called a low mass star. Okay, and anything that is more massive is called a high mass star. And let's see what else. We actually talked that all stars start out as a protostar, which basically is a little warm nubbin, and then they go to be, when they first turn on, they become a main sequence star. And that might ring a bell or two, because actually our sun is a main sequence star, and as a main sequence star they are fusing hydrogen in their core. Both sizes of stars do that. Okay, and then actually they will move on the main sequence. To me, whether they're low mass or high mass, their next stage is actually, this semester I'm just calling it the giants. And on the HR diagram, that's kind of the upper, like above the main sequence, the giants. Okay, so just to kind of put things in perspective. We talked, I think, about how low mass stars actually end up as white dwarfs. I think we talked about that. After they're giants, they end up as white dwarfs. Seems so long ago. Okay, and actually high mass stars, I think I've already given you a hint that high mass stars explode in supernova events. Again, this is for me too, because I'm not sure chapter 13, chapter 14 what we talked about, but I think that's kind of how we left it. So that's kind of the big picture. Okay, so actually now we pick up in this chapter with kind of the end of stars' lives. The end of stars' lives, focusing on that. And this actually is a look at a white dwarf more in close detail. We said that the brightest star in our nighttime sky is Sirius. They're Sirius. We said that most stars actually have a companion. They were born about the same time, and they're gravitationally hanging out. Their Sirius A is really bright. Sirius B is actually a retired white dwarf star. So a little bit more about white dwarfs. I think the video, they kind of mentioned this. A white dwarf is very compact, very dense. But a white dwarf is still normal atoms. And what normal atoms means is if my fist is the nucleus, the center of an atom, we talked about how electrons are around the nucleus of an atom. So normal matter is basically, if you have 2 atoms, they won't squish together because the electrons that around each of them will say no. Okay, that's called electron degeneracy. So we still have that going on in white dwarf. But a teaspoonful from the white dwarf would weigh 15 tons on Earth. So it's very compact. One of the odd things about the white dwarf is the more massive it is, shown over here on the far right. The more massive it is, if you have a white dwarf, it's 1.3 times the mass of our sun. It actually has a smaller volume, which is kind of weird. And it has a smaller volume because it has more mass. Okay, gravity has made it smaller. So, but there is a limit to basically how normal matter can stand up. So basically you have atom, electrons are making it so they don't squish together. Now, if you take a white dwarf and you make it massive enough, basically something's got to give. Now, as you make something more and more dense, as electrons occupy a smaller space, they are going to go faster and faster. But the electrons cannot go as fast as the speed of light. So this all kind of says that there's a limit to the size of the white dwarf you can have. A white dwarf cannot be any larger than 1.4 solar masses. So there you go, 1.4 solar masses. It's a limit to how massive a white dwarf can be. That's called the Chandra limit. So at the end of chapter 13, we had a slide that actually looked at how a pair of stars that are hanging out together, actually, if one is very swollen, it can dump material on another one. And actually, that's what's being shown here. I think we called this actually maybe an accretion disk. If we didn't, it's coming up. So anyway, this is a binary stars. One is giving mass to the other. It can happen, right? Because in this giant stage, it very much can happen. In this scenario, that other one is a retired star. It's a white dwarf. And the video talked about this too. So when the retired star, the white dwarf, gets new material, a few things can happen. Two major things I want to talk about. So one of the things that can happen is actually, and it's called an accretion disk, and we'll talk more about accretion disks. All an accretion disk is, and I think your textbook uses this analogy, is if you have water going down your bathtub drain, if you watch it carefully, it kind of makes like a swirling before it finally goes down your drain. That is like the accretion disk. And your drain would be the white dwarf. Okay. Now, stuff isn't going to fall down a white dwarf, but stuff is coming towards a white dwarf. And it goes faster and faster as it gets closer to the drain or the white dwarf. Now, all that commotion actually creates friction, which kind of creates some heat around this, what we call accretion disk. So there is definitely some energy coming from this, thermal energy coming from this retired star that otherwise wasn't because of stuff being dumped on it. So there's two scenarios that can happen when this white dwarf gets dumped on. The first scenario I'm going to talk about is nova. Now, we already kind of talked about a supernova. Supernova is when a massive star blows up. Okay, nova doesn't have the super, so it must not be as cool. Okay, and so actually a nova event has a white dwarf being dumped on by a companion, like you see here. The blue is the white dwarf. Of course, the red is the main, or not a main sequence, but the giant star. What is being dumped on the white dwarf is fresh hydrogen. So basically this fresh hydrogen coming from the companion, and we said the accretion disk can get nice and hot. Specifically, in the accretion disk, it can get hot enough to begin nuclear fusion. You're like, really? Yeah. So basically, you have hydrogen fusion going on in the accretion disk. And it just kind of does a blip, and then it's done. That's a nova event. So nova event doesn't really affect the white dwarf itself. It's more, like I said, kind of in the accretion disk or on the surface of the white dwarf. You got fresh hydrogen. So this is showing you the results of a nova explosion. So the white dwarf is intact. So now I get to talk about another scenario, again with the white dwarf, okay? But now the white dwarf gets more matter, think of it this way, more matter than just enough to go ahead and have nuclear fusion in the accretion disk. Basically, the matter it gets bumps up against that 1.4 solar masses, that Chandrasekhar limit. So what a white dwarf is, and I think we probably talked about this in chapter 13, but if we didn't, here it is. A white dwarf basically is kind of a carbon orb, because a white dwarf is actually helium has been, in the center, helium has been fused together to make carbon. So in this case, it basically begins carbon fusion in its core, and that white dwarf was never meant to do that. Okay, so the problem with it now coming alive with carbon fusion is that it doesn't have kind of the bulk of what it was when it was a regular star. So fusion occurs in this low mass star, this white dwarf that got more matter, and basically it blows itself up. It's kind of its last hurrah. So this type of, and unfortunately they call it a supernova also. You're like, really? Could you not have called it something else? Because this is so similar to the massive star blowing up. Okay, it's a different type of supernova. What I'm going to be doing is calling this the white dwarf supernova. Okay, the other one I'm going to call the massive star supernova. But just for the record, you see the type 1A? This is how I learned it, which is even a little more confusing. There's two types of supernova, okay? The type 1A is the white dwarf supernova. The type 2, here in a minute, actually is the one we first learned, where a massive star blows up. Don't blame me. Okay, so yeah, it's where a white dwarf comes out of retirement and blows itself up. So kind of then summarizing the whole two types of supernova, and it is frustrating. But the massive star supernova we first talked about, it's something more massive than 8 solar masses, it's a main sequence star anyway. That's called a type 2. And then the one we just talked about, when a white dwarf has a companion that's dumping on it, okay, and it gets to that 1.4, approaches 1.4 solar masses, then it blows up because it has nuclear fusion going on in its core. So it's a subtle thing, and this semester I'm definitely not testing you over it, but you might be saying, well, if a supernova occurs in outer space, how do we know which one it was? And there are a couple of ways of doing that. One is to watch the decay curve. So actually all this is how bright did the supernova event, was the supernova event in units of luminosity, and then how did it decay over time? So like I said, it's kind of a subtle thing. It's looking like the white dwarf supernova is more luminous, okay, but kind of decays at a different rate than the type 2 supernova. So that's one of your things to figure out. I think you'll do okay as long as if you hear me say a white dwarf supernova, you know, or supermassive supernova, or excuse me, if I say massive star supernova, it's the first one we talked about. The other thing in this material we just covered, you need to differentiate between, is the nova and supernova that both involve the white dwarf, okay? So the supernova, the white dwarf supernova are much more luminous than if it just basically burps, has fusion going on in its accretion disk, which is a nova. So the supernova white dwarf supernova are a lot more brighter than just the regular old nova. Okay, but to me this is a big thing. I mean, if you're a white dwarf and you're looking for longevity, okay, you want to go nova, not supernova. Say a white dwarf that does a nova event basically can do it again and again and again because it leaves the white dwarf intact. So the other thing, or this is actually to kind of differentiate between the white dwarf supernova and the massive star supernova. The massive star supernova, we're going to talk more about this, but when a massive star blows up, it leaves behind a neutron star or a black hole. Okay, when a white dwarf blows up like this, nothing. Okay, nada. So that's another good distinction. So that's the whole, that kind of ends my saga with white dwarfs with a binary and things that can happen. So to take a closer look at the type 2 supernova events with this, where a massive star ends its life, okay? I think the video did a good job kind of showing you what leads up to it blowing up. But one of the things we said could be left after the supernova is a neutron star. So we need to talk about neutron stars. So the word neutron and neutron stars kind of gives it away. I think we talked about this maybe before. A neutron star is where it's not normal matter. It's totally not normal matter. Because basically instead of having atom A and atom B with their nuclei and their electrons around there and they bump up, okay, basically a neutron star has had so much gravity pulling in on it that the protons in the nuclei have combined with electrons to form neutrons. So it's like neutron soup. Okay, so instead of electron degeneracy holding up that matter, it's what we call neutron degeneracy, which can hold even more pressure. Okay, we're actually going to say that neutron degeneracy can support the weight of a neutron star up to about 3 solar masses. So how do we know about neutrons? And there's kind of a cool story behind these neutrons, excuse me, not neutrons, but neutron stars. How do we know about neutron stars? There's a cool story back in '67 where they got this this kind of ongoing pulse. You can kind of see the signal. Ding, 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 okay? And at first they thought that, oh my gosh, and this is from outer space, they thought that intelligent life was trying to communicate with us, like Morse code or something, very regular. And so the people at NASA must have a sense of humor, because historically they called these LGM sources, LGM, and that stands for Little Green Men. I know, right? But if you think of what we know now versus what we knew in '67, so I just think they probably giggled the whole way. But so they found this beep in radio signals. So like, all right, this energy.
That had to have been kind of a scary kind of thought too.
That would be. Yeah, I know, like Stephen Hawking and different people have said, what if there is intelligent life that is communicating / visiting us? What ramifications is that on our civilization? Run! Where to, I don't know. But, so as it turns out, actually, these which we actually now call pulsars, that's what that is, okay, actually are created from the presence of a neutron star. So what you're looking at here, actually, if you've looked at my recordings, I have a little icon for this class, and it actually is, it's supposed to be a supernova. It's like a picture of this. I don't know if you recognize it, this. And the guy's got a cape, and yeah. So actually, this was a star that blew up a long time ago. I can't remember, 1,000 something, I think. But this actually is the guts of a star. This right here, this is a supernova remnant. I think I had that supernova, star blew up. What's left? A remnant. Actually, this particular supernova remnant is Messier object number 1, and it's called the Crab Nebula. Looks like a crab. Anyway, hiding in that actually is a neutron star. So somewhere in there is a neutron star. Makes sense. Supernova remnant, neutron star. So this is actually from the Crab Nebula. This is visible energy. Jeep, 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 jeep. But it's not that slow. Like 0.033 seconds between these blips of visible light. So how does that work? How do we get these signals from a neutron star? So, and I think the video addressed this, I'm sure it did. We get those pulsars from a neutron star because of this. Basically, a neutron star is kind of the nugget of a regular star. One of the things about stars, including the sun, is they spin on an axis. Now, as the star lived its life and converted gravitational potential energy to kinetic energy, got smaller, it's kind of like an ice skater bringing in her arms, or his arms, went faster and faster and faster. So this neutron star is spinning crazy. The other thing is that if you get charges rotating, you can create a magnetic field. So actually here, kind of these ghosty looking things, is the magnetic field around this neutron star. In this case, though, notice it does not coincide with its axis of rotation. So this is its axis of rotation, but its magnetic field kind of goes like this. So what happens is as it spins, it basically kind of whips around like this. It's kind of called what we call the lighthouse model. Okay, so the way it's a lighthouse model is, here's your lighthouse. Okay, this would be the axis of rotation of the neutron star. And then this beam of energy actually is kind of the tilted beam of the kind of squirting out the ends of the magnetic field. So it sweeps around. It goes, you see it, and then you see it, and then you see it, and then you see it, that sort of thing. So you're like, all right, so I see this energy kind of coming like this. What is the object that's emitting that energy? Well, if you narrow down the characteristics of that object, you can see that it's spinning very fast, it's relatively small, and it's very dense. And so it's not normal matter. It's a neutron star. All right. So now we're switching it up. I know it looks like the same picture, because it is. But now, instead of a neutron star here, now instead of a white dwarf here, we're going to put a neutron star. So here we have a pair of stars that have lived their lives. Okay, actually, this one is still living its life as a giant. Okay, and this one actually is, in the center there, is a neutron star. But you figure it's very similar. Basically, matter from the swollen giant can dump on the neutron star and create an accretion disk, kind of like we saw with the created a nova and or a supernova with a white dwarf. Similar to the nova event, what can happen within the accretion disk is actually it can get very hot. This is another look at kind of the accretion disk, looking at it face on instead of kind of more edge on. So this can get very hot, and the matter actually can, fusion actually of the matter again can create these little burps of energy. Now, here's where I'm hoping you guys remember the difference between our energies. Okay, so light energy is one thing. More energetic than light is ultraviolet. More energetic than ultraviolet is X-rays. Here in a minute, we're going to talk about another event that actually is even more energetic. Beyond X-rays would be gamma rays. So that's an indication of kind of the magnitude of the energy that's released. So I already mentioned this kind of 3 solar masses thing. The thing about it is that neutron stars have an upper limit for the mass that they can support. If there are more than 3 solar masses, that neutron star, the neutron degeneracy of the neutrons can't keep up its mass. Okay? So in that case, something else happens. And that something else is something kind of strange. Basically, the matter of the neutrons then collapse and form what we call a singularity, which is basically the center of a black hole. Okay, so again, if the star blows up, supernova type 2, okay, massive star ending its life, and the thing that's left is more than 3 solar masses, the darn thing's going to keep shrinking down. Basically, neutron degeneracy won't hold it up anymore, and it will become a black hole. And the way I think of it is all the matter basically goes into kind of an infinitely small object, okay, called singularity. I don't know about infinitely small. So we've been talking about anything greater than 8 solar masses we said was a high mass star. Now actually, if you want to in your own mind, think, all right, well then 25 solar masses or greater, that's a high mass star. So in other words, anything greater than 8 solar masses, you're going to get a supernova. Okay? Then if it's between 8 and 25, you're going to end up with probably a neutron star. Okay? If it's between 25 or we said 150, right? We said there's an upper limit to a star, then it's going to end up as a black hole. But there are different ways of creating black holes. This is just one of many ways of creating a black hole. Right. I think, let me double check. Get your slides. Thank you. Okay, thank you. Debating where to. Let's do a little bit more about black holes, but I don't think we're going to get all the way through this chapter. So, a black hole. I already kind of told you, basically squish down, okay, beyond neutron degeneracy to support the object. You can turn anything into a black hole. I think I might have mentioned before when we were talking about subatomic particles that there's this thing called a particle collider, which a famous one is the Hadron or the HLC. Anyway, you basically take, the one I'm thinking of is around Paris, okay? So they have a track that goes around the whole city, and basically they accelerate particles to run into each other. So they take a pair of particles and they go in opposite directions, okay? And they make them go faster and faster and faster. They have like things along the way to make them go faster, 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 faster. And then at one point they'll run into each other. My point here is that when that came online, or that technology came online, people were afraid that you could actually take particles, squish them together, and make a black hole. Because there's something to be said for that. That's all you need for a black hole. So actually, I have some examples of turning the Earth into a black hole. Could you do it? Yep. Could you turn the sun into a black hole? Yep. Pet black holes, I don't know if I'm really kind of seeing that. Okay. But all kidding aside, the other types of black holes, and actually in Unit 5, we're going to talk about the black holes that are in the center of galaxies. The Milky Way galaxy, our galaxy, has a black hole. Actually, it's called a supermassive black hole. Okay? Most galaxies have a black hole. Okay, what does that mean? Basically, matter has squished down to the point where neutron degeneracy cannot support it. Okay. Now, I think of black holes as, like I've described here, basically they've created a hole in the fabric of space and time. Now, Einstein, which I don't really go into much, but Einstein described kind of space and time as bless you, as basically being one entity. So as I'm walking around the room, of course there's a time and there's a space that I'm occupying. They kind of go together. So Einstein said in that sense, when you monkey with space, like black holes or massive objects, you also kind of have a time element, and we do see that. Einstein had theories then that came from that. But here we go. So the space and time actually are kind of combined into a common fabric. So all objects, I know it doesn't seem like it, but all objects as we walk around, it doesn't have to be on Earth, it can be anywhere, we are actually kind of creating our own little kind of dent in the fabric of space and time. The more dense an object is, and density is basically taking stuff and squishing it together. The more dense an object is, kind of the more it affects, it has an effect on the fabric of space and time. I've heard it likened to this: if you have two people and you have like a sheet, and you hold a sheet, like a bed sheet in between you, you can put objects on the sheet and it makes a little dent, okay? Basically, your sheet is the fabric of space and time. If you were to take like something dense, like a metal ball, like a very dense, put it in the middle, it would go like that, okay? If you took something of a slide, it would make it. So black holes basically go ahead and make a hole in the fabric of space and time. So does this not look like you could go to another universe through this? A wormhole? Okay. There actually are, some scientists that are thinking along those lines. But in the notes, we're going to talk about what happens when you fall through a black hole. So that might be problematic. So, like the slide said, or like the video said, why do they call them a black hole? Well, the thing is that if you go what we call beyond it's called the event horizon. If you're on the inside of the event horizon, okay, and you want to leave, okay, you'd have to go faster than the speed of light to leave the gravitational influence of the black hole. That's the problem. So one of the things we kind of briefly talked about in here is there's this thing called escape velocity. Okay, escape velocity for Earth is like, I don't know, I need to look it up, like 11 meters per second. So basically, if you are going 11 meters per second, if that is our escape velocity, 11 meters per second or faster, you can get away from the gravity of the Earth, okay? So the thing about escaping a black hole is you have to go faster than the speed of light. Okay? So escape velocity can be calculated this way. So the way you read this is if you want to calculate how fast you need to go in order to escape, let's go ahead and make this our planet that a person is on. Here's our person. Okay, and how fast do they need to go in order to escape the gravitational influence of the planet? So what you do to calculate how fast they need to go is you take 2 times G, yeah, that's a constant, that's the gravitational constant. I think we looked at that briefly before. 2 times the mass of the object that's holding them there. So in that case, that would be the mass of the planet, mass of the object they're leaving. OBJ for object they're leaving. And this actually, R, is the radius, and that is the distance, distance between U and center of mass. Okay, so in the figure I've drawn, does this make sense? The radius would be here. That's my R. So if we were to take that particular example, and if you make R smaller and smaller and smaller, so we're taking it like a planet, and we're going to shrink the planet down. Okay, so then my R becomes smaller. If I make my R smaller in this calculation of escape velocity, if R is smaller, does it make sense that escape velocity gets larger? Because we're dividing by R. So we're dividing by a smaller number, so escape velocity goes up. So you decrease R, you increase the escape velocity required, the minimum velocity, okay? So here's the deal. If I make that R term small enough, okay, it's possible that my escape velocity goes all the way up to the speed of light. And that's kind of what we're talking about here. Same mass, we're just making it smaller. So here was the example, and I must have gotten this from the internet or from your textbook or something. But if you were to take Earth, okay, the same, keep the mass of the Earth the same, basically shrink it down so that the radius, so from the center of the Earth out to the edge, is 1 centimeter. Okay, so they make like the, so the diameter would be 2 centimeters, but 1 centimeter would be the radius. Now that's kind of strange to think about, but in that case, if you were small enough to stand on that 1 centimeter radius Earth, okay, you'd actually have to exceed the speed of light to leave you've created a black hole. That's it. That's it. All right. So let's go ahead and leave this slide leave the last few slides for Monday. That way you guys don't have to do chapter assignment either. Okay, so we'll finish up this chapter on Monday, and we'll have a review session on Monday, and that will be that.